it's Akhirah. Now we're on Unit 6, Chemical Bonding. Okay, so basic concepts. Okay, so we have 12 basic concepts, right? So, when two elements join together, a compound is formed, right? And then atoms combine as a result from when they transfer or there's a shift in their valence electrons. Or I guess share, the valence electrons, right? So, when a shifts or a transfer of electrons occur, force of attraction develops. Creates, develops, whatever. Right. And then this force of attraction, when the shifting electrons occur, this force of attraction that holds the atoms together, this is called the chemical bond. This is called the chemical bond. Okay? And then the process is called chemical bonding. Wow. So fun. Right? And then when chemical bonds form, right, a chemical reaction has to take place for the chemical bond to form. Okay? Okay, number 7, energy, right? So energy is required for any reaction, right? And then potential energy, is stored in the bonds of a compound of two elements, right? And then when a bond is broken, it's endothermic, this potential energy is absorbed. Wait, what? Well, pretty much when bonds break between two atoms, it's an endothermic reaction, energy is absorbed, right? But then when a bond is formed, it's exothermic and it releases energy. Okay. So there will be a decrease in the potential energy, right? And the more energy that is released, the more stable that the new compound would be. So the more exothermic a reaction is, the more stable the compound is. And then an acronym you can use is BARF. So breaking means absorbed, and then released means formed. So the breaking of bonds absorbs energy, and the releasing of energy is when bonds are formed. Okay. Number 8, bonds take place if the bonding leads to more stability, a lower energy state of an ordinary couple. Fair. Oh, I love that gift so much. And then, yeah, so these bonds will just kind of happen if, it's more stable and there's a lower energy level, state, whatever, right? Then monatomic gases, I'm definitely not saying that correctly. These are group 18 gases, so these are your noble gases. They have a completely filled valence electron. They have a stable octet, so 8 valence electrons. And then pretty much noble gases pretty much never form compounds. Well, there's a few exceptions, but pretty much never form compounds. And then this is why, is because the 8 valence electrons, very stable octet. Yeah. And then all the other elements usually have valence electrons of about from 1 to 7. Good. Number 11, electrons shift to form stable octets. So these electrons will move, so an element can have 8 valence electrons, or 2, depending if it's like hydrogen or something, right? And then in bond formation, atoms will usually attain a stable electron configuration, like how noble gases have 8 electron, or 2 if it's helium, 8 valence electrons, right? Ooh, bonding. Yeah, so pretty much when bonds form, the atom just want 8 valence electrons. Okay, now bonding. Lewis dot structures. Okay, so the dots on the Lewis dot structure, right? These dots represent the number of valence. Oh my god, my ear hurts so much. I should really get that checked out. Pretty much, the dots represent the valence electrons, and then the symbol just represents everything else. And also represents what atom it is. So P would be for phosphorus. You would think that I've looked at the periodic table so many times. I would know which symbol represents each element. No, I don't. I still don't. Whatever. Right. Lewis dot structure. So the correct order to fill in the dots is to make a pair with the first two electrons, then fill each one on each side before we pair up. Okay, so how do you fill in the dots of a Lewis dot structure, right? So these two top are a pair, right? They kind of go around in a circle. 3, 4, 5. That's a bug. That's annoying me. Then once you do one circle, you do another circle. 6, 7, 8. That bug's gonna be though. Where is it? Okay. Oh, the Lewis dot structure of ions. Oh my god, why do my ears hurt so much? I am about to lose my mind. Okay. So, if you're drawing the Lewis dot structure of ions, so how do you do it for a metal? For a metal, you would draw the symbol. So the one that's shown, Na, sodium, right? So you just draw Na, or write Na. You don't really draw letters. You would write an Na, right? And then there would be no dots. Actually, the reason there would be no dots is because in a chemical reaction, metals almost always, I'm pretty sure. There could be an exception because it's chemistry, and chemistry loves exceptions, but almost always they lose electrons, which is why there would be no dots. But there would be no dots, and then you would show the correct charge, which is usually positive. So you would show the correct oxidation state, positive. Well, not the number, just the number, right? Not the number, just the charge. Holy god. Okay, and then for nonmetals, so first you would draw the symbol. So for F is fluorine, right? And then you would draw 8 dots, and the reason you draw 8 dots is that in a chemical reaction, they would take electrons to form 8 valence electrons. So you would draw in 8 dots, and then you would add brackets. After you draw the electrons, you would add brackets around it, and then you would have a negative charge, because typically nonmetals have a negative charge. Okay. Types of bonding. There's 3 types of bonding. You have ionic bonding, you have covalent bonding, and you have metallic bonding. And there's different characteristics between these things. Okay. So ionic bonding forms when a metal and a non-metal bond, right? So what are the characteristics of ionic bonding? They have high melting, and they have high boiling points. They're electrolytes, so they are very good conductors of electricity when you dissolve them in water, and they have very, very, very strong bonds. Covalent bonding is when two nonmetals bond. They have low melting points and low boiling points. They're non-electrolytes, so they are not good conductors of electricity when in water. They have weak bonds, at least compared to ionic bonds, right? And the metallic are bonds between metals, and then they have the properties of metals, so they're conductors, they're malleable, they're ductile, all that fun jazz. Okay. So ionic bonding is formed by the complete transfer of one or more electrons. There should be an S there. One or more electrons from one atom to another. Ionic bonds are formed when an atom completely transfers from one atom to another, and these are usually metal and non-metal. Okay. I feel like oh, I guess not. Okay, ions. So this is our charged atom or particle, right? Ions are formed when an atom gains or loses an electron, right? So metals usually lose electrons and they form positive ions, right? Positive ions are called cations, and the way you can remember cation is, I'm sorry, that's so fucking cute. I'm sorry. Look at that drawing. That is so. I'm getting distracted. Okay, so a way you can remember that positive ion or cations is cat ion has a T, and you can think of the T as a positive symbol, positive sign, plus sign, whatever, right? But yeah, so they would lose electrons, and then hence they would have positive ions, metals, yes. And then non-metals, they are anions, right? So they will typically gain electrons, and they would form negative ions. Right, and then a way you can think of negative ions being anions is that anion, they have N's in them, and then N is for negative. That's one way you can think of it. Okay, electron configuration. So potassium has electron configuration. If you look on your periodic table, 2-8-8-1. Okay. So when it loses an electron, what's the new electron configuration? 2-8-8. Okay. And then when you look at the periodic table, which element has the configuration? So which element has the electron configuration of 2-8-8 will be argon. Ar. So potassium with a positive charge has the same configuration as argon because it has lost an electron. Okay. Now try chlorine. Okay, that's wrong. It hasn't lost an electron, it has gained an electron. I was a bit confused. I was reading that, I'm like, that doesn't sound right. It's gained an electron. So chlorine, it will gain an electron, and then it'll have the same electron configuration as argon. Since it has gained an electron, I didn't make these PowerPoints. Don't blame me, okay? Ionic bonds and equations. Na and Cl. Lewis dot structures, symbols, structure. Lewis dot symbols. Ion formation. Fuck, my brain's not burning. And then a compound is formed, right? Okay, oh god. Doesn't show you, so I gotta actually. Okay. I don't have space to show you. Okay, whatever. So. So NaCl, sodium has 1 valence electron out, and then chlorine has 7, right? And then Na has an oxidation state of +1, Cl has an oxidation state of -1, right? So, and then a compound is formed, and then what it means is if the charges add up to 0, you don't play crisscross. That means +1 -1 is 0. You don't gotta do the whole crisscross thing, because then the thing is just gonna be NaCl, right? And then when you're doing the Lewis-Strauss structure, you want to make the ionic diagrams. So for Na, it will just be Na plus, right? And then for Cl, it will be Cl with 8 dots around it. The brackets with a minus. Yeah. So bonding. Oh, okay, Cl. Okay. Crap. Okay, it doesn't show you. Okay, so pretty much. No, actually, I'll just explain to you on the next slide. To find a formula of a compound, you will use the crisscross method. So what's the crisscross method, right? So you would write the symbol in the oxidation state of the metal. Lower electronegativity if they are both. Crap, what does that mean? Shit. Whatever. Pretty much you would write the oxidation states of both of the elements, right? Oh, I know what it means. So pretty much lower. Okay, so. Right, so, well, this one shows between 2 nonmetals, so carbon and oxygen. So you would take, for the carbon, you would take the lowest oxidation state, so +4. Oxygen only has 1 oxidation state, so -2. You would take those, and then you kind of swap them out, right? So carbon is going to get the 2 from the oxygen, you drop the signs, right? And then oxygen is going to get the 4 from the carbon, right? So that's the crisscross, C2O4. But you can reduce. The 2 and 4 have a common GCF of 2. So you would divide each by 2 to get CO2. Okay, ionic bonds and equations, Li and S. I don't want to go through this whole thing, but I mean, I guess you can if you want to. But I don't think it really matters. It's just this again. Okay, electronegativity, table S. So what does electronegativity? Electronegativity is how strong an atom attracts electrons, right? So metals have a low electronegativity because normally when they form bonds, they lose electrons, and nonmetals have a high electronegativity because typically when they form bonds, they gain electrons. Electronegativity difference. So pretty much you would find the electronegativity numbers on table S, right? So this is used for the prediction of a bond type and the ionic character, right? So the higher the difference between two electronegativities of two different elements, so is usually that means that there's more ionic characteristics and it has a stronger bond. So usually the difference, this is just a generic rule, is implied all the time, but a generic rule is that if the difference between two elements, if their electronegativity difference is equal to or greater than 1.7, usually ionic. If it's less than 1.7, then it's usually covalent. So NaCl, well, I'll go through it with you actually. Yeah. So NaCl, Na has electronegativity of 0.9. Cl has electronegativity of 3.2. So 3.2 minus 0.9 is 2.3, which is greater than 1.7, which means it's ionic. So I guess give CO2 a try. Okay, so CO2. So carbon has an electronegativity of 2.6. Oxygen has an electronegativity of 3.4. 3.4 minus 206, 0.8. Lower than 1.7, so it's covalent. I feel like did I skip anything? No, I didn't. Okay. Ionization energy, table S. So this is the amount of energy that is needed to remove the most loosely held electron from a neutral atom. Hold on, I'm gonna turn off my AC because I am literally freezing right now. Ugh. There we go. Okay. So it's the amount of energy that's needed to remove an electron, the loosely held electron, from a neutral atom. Okay. So the greater the force of attraction between the positive nucleus and a negative electron, the higher the ionization energy. So pretty much, how do I explain this? So typically, like, if the electron is farther away from, the nucleus, so like if the atom has more energy levels and the loosely held electron is farther away, so there's a less force of attraction between the nucleus and the electron, so it will have a lower ionization energy compared to like hydrogen has one electron, right? I would assume so. Yeah, one electron, which is like practically right next to the nucleus. So they have a very strong force and it takes a lot of energy to remove that one electron. So the first ionization energy is the amount of energy to remove the first electron, and then metals usually have a higher ionization energy compared to non-metals, because, yeah, they do. I don't know why, I'm trying to think of why, I can't remember why. Whatever. Properties of ionic solids, right? So ionic solids, they have pretty strong bonds, and they have high melting points. They have a crystal lattice structure. I'm definitely not pronouncing that correctly. Apologies. Right? So that's the structure. They don't conduct electricity in the solid phase, but they do conduct electricity if they become a liquid or if they are placed in water. And they're also very hard, solid substances. Okay. Covalent bonding, which is also known as molecular bonding. Covalent bonding is when two nucleuses, that's not English, two nuclei share an electron, then than rather transferring it. They share one. Okay, right? So they form a molecule. A molecule is anything that is any substance that has covalent bonds, that is covalently bonded. Um, usually this takes place between nonmetals, and usually carbon. Carbon is in a ton of covalent bonds, a lot. Right. So there's three types of formulas when it comes to covalent bonds. There is the molecular formula, there's the electron dot formula, and then there is a structure formula. And then a structure formula shows like a bond as a line, and that shows a shared pair of electrons. So electron dot diagram, it shows that electrons are being shared. It's similar to the Lewis dot diagram for ionic compounds, but there's no charges. And you have to make sure that each electron has 8 valence electrons or 2 valence electrons if it's a hydrogen or helium. But I don't think, well, helium is a noble gas, so it's not gonna be whatever. Right? So here, for hydrogen and chlorine, hydrogen will have 1 valence electron, chlorine will have 7, and then they bond, they share this electron, and it shows that this electron is being shared between these. It shows that these 2 electrons are being shared. Yeah. And then same for H2O. Hydrogen has 1, oxygen has 6, and then you see that these are being shared. Structural formula, it has the same rules as the electron diagram. Instead of showing dots to show that they're sharing electrons, it shows a line instead. And each line is a bond, and each bond has 2 electrons being shared, right? So HCl again, we have a bond of 2 electrons, and then we have the 6 here, because these are not being shared with the hydrogen, they're by the chlorine. Oxygen, so when oxygen bonds to itself, it has 2 bonds, they're sharing 4 electrons, and then each oxygen will have their own 4 electrons. The nitrogen, when it bonds with itself, creates 3 bonds, so they're sharing 6 electrons, which are shown here. Then you have these 2 only, just vibing. Yeah. Diatomic molecules. Diatomic molecules are 2 of the same atom covalently bonded, right? So we have 7 diatomic molecules that you have to have memorized. You can use it by using Brinkelhoff. Brinkelhoff, so, oh crap, okay. Brinkelhoff, where is my, so you have Br, which is bromine, yes. I, iodine, N, nitrogen, Cl, chlorine, H, hydrogen, O, oxygen, and then F, fluorine, right? So in diatomic, you have single bonded diatomics, which means there is only 2 bonds between the 2 atoms. The single bond diatomics are hydrogen and bromine, fluorine and iodine, and chlorine. Is that it? That's it. Okay. I don't think you have to memorize that, but I think it's still good to know. Double bonded diatomics, just oxygen. Oxygen's the only one. And then triple bonded will be nitrogen. I'm pretty sure that's it. Yep, that's it. Okay. So you just you have to know your diatomic molecules, right? So you gotta know all of them. Types of covalent bonds. You have a non-polar covalent bond. So a non-polar covalent bond is electrically neutral, right? So the electronegativity difference between the 2 atoms is 0, right? And then that means the electrons are shared evenly between the atoms in the covalent bond. And then the elements on each side of the bond are the same, so, which is for diatomics, yeah. And then you have a polar covalent bond where the electrons are not shared equally. So usually the electron negativity difference is greater than 0 and is less than 1.7. Well, usually it's less than 1.7. General rule. And then the elements on each side of the bond are different. And then the electron dot formula can show changes in this, the electrons not being shared equally. Snap. Snap represents symmetrical nonpolar, asymmetrical polar. Why am I snapping? I need to stop snapping. Oof. So a nonpolar molecule. This is types of covalent molecules. Okay, so a nonpolar molecule is formed using polar and nonpolar bonds. And the reason it's a nonpolar molecule is because it's symmetrical, right? So example would be diatomic, CO2, a tetrahedral, which is 4 of the same element combined to attach to a carbon. So methane, CH4, and then carbon tetrafluoride, C4H. C4H, okay, right? So, it's a nonpolar molecule, which is different from a nonpolar bond, to be clear, right? So, like a nonpolar molecule, CH4, right? It's a nonpolar molecule because it's symmetrical, right? But it has polar bonds because the bond between a carbon and a hydrogen is polar. Yeah. And then a polar molecule can only have polar bonds, right? And then there's no symmetry, right? And it forms a dipole. So and then the diagram has to show the chart. So you have water, H2O, and then you have ammonia, NH3, right? Oh, okay. Well, they're not symmetrical. Yeah, they only have polar bonds. So, summary: you have covalent bonding, which can form nonpolar bonds and polar bonds. Nonpolar bonds, polar bonds can be in both nonpolar and polar molecules. Nonpolar bonds, they can't be in polar molecules. They can only be in nonpolar molecules, right? So, and examples of that: nonpolar bonds and nonpolar molecules, diatomics. Polar bonds and nonpolar molecules, CO2, tetrahedrals, right? And then polar bonds and a polar molecule, you have H2O and NH3. So shapes of covalent molecules. So you have a linear shape, which is literally just atoms in a straight line. So you have diatomics, so O2, H2, Br2, right? Or and you have CO2, right? Then H2O or H2S. So pretty much you're going to have one element here. So like an H2O, it would be hydrogen, and then the oxygens are kind of going to bend outwards. Bend outwards like that. Same for H2S. And then you have triangle, tripod, a pyramid, NH3. How do I... Pretty much you would have, like the end would be on top, and you would kind of have 3 bonds of hydrogen kind of forming like a triangle shape, like a pyramid shape. And then tetrahedral, CH4, C4H, CH4, C4, CF4. Oh, God. No brainy. What does that look like? Pretty much you have a central atom, and then you have like bonds going off, like one at the top, one at the bottom, one to the left, one to the right. Yeah. And tetrahedron, tetrahedron looks like whatever. So what are the properties of molecular solids? Molecular solids are soft, they are very poor conductors, they have low melting points, they're like candy. I mean, candies are molecular solids, so that's one good thing of it. Now I really want candy. I could really go for some gummy bears right now. Actually, are gummy bears halal? Most of them aren't. Anyways, I say my existence isn't even halal, so who cares? Anyways, network solids, which are covalent crystals, right? So there are macromolecules, huge molecules pretty much, that have covalent bonds, which extend from one atom to another in a 3D form, right? So they're pretty much ionic wannabes. They have, pretty sure they have some properties of ionic things. Yeah, they have some properties, but they don't at all, right? So examples of these network solids are diamonds, graphite, and sand, right? So they're hard and they have high melting points, but the reason that they're not, like how they are different from ionic solids is that they are poor conductors of heat and electricity. Polyatomic ions on table E, right? So polyatomic ions are 2 or more covalently bonded atoms that remain together during a chemical reaction, right? So these covalently bond groups, they have an ionic charge. So they act as like an ionic thing, an ionic whatever, as like they act as one thing in an ionic bond. Whew, that's a lot of words, right? So usually they would end in ATE or IT. So sulfate's one of them, carbonite's one of them, sulfite is one of them, nitrate is one of them. So there's more. So formulas that contain a polyatomic ion, they have both ionic and covalent bonding. The covalent bonding is within the polyatomic ion, and the ionic bonding is with the polyatomic ion and whatever else is in said formula. So Na2SO4. So the covalent bonds are in the SO4, and then the ionic bonds are between the Na2 and the SO4. So pretty much it's the same thing. You would do the crisscross method. So, oh, doesn't even show you. That's great. Okay, you know what? I'll just give the first one to you, and then you can do the other three by yourself, right? So, if I was doing this, let's do crisscross. Ca has a charge of +2, right? And then NO3, where's NO3? NO3 has a charge, crap, we just lost it, -1, right? So you would play crisscross. The one's going to go to the Ca, the two is going to go to the NO3. So you have Ca, NO3, 2. Okay. So do the rest, I guess. I'll give you guys, like, I think 3 minutes is enough. I'll give you 4. 4 minutes. So when you do the crisscross method, Na and CO3, you have Na2CO3, NH4 and SO3, you get NH4 parentheses 2. Oh yeah, that reminds me, for polyatomic ions, right? When you're making a bond with them and you have more than one polyatomic ion, you want to put the polyatomic ion in parentheses and then put the subscript outside the parentheses. I don't know if I mentioned that, but so it'd be NH4 parentheses 2 SO3. And then for H plus and OH minus, it would be HOH. Okay. Metallic bonding. Metallic bonding is an attraction force that binds metals together. So, an example would be mercury with mercury, so any sodium. Ugh, I feel like that's a really dumb question to ask. I'm pretty sure it is sodium. Sodium with sodium, and then Pb with Pb. Pretty sure that's lead. Could be wrong. I need to check because I said that. Nope. Wait, no. That's not even look at the wrong one. Right one. Pb, where are you, Pb? That's a good question. It is lead! Subrotation time. Anyways. So, the way that these metals are bonded together is that valence electrons pretty much belong to the whole crystal than to individual atoms. The valence electrons are going wherever they want to, okay? They're not bonded to a single atom. So pretty much these positive ions of the metal are immersed in the sea of mobile electrons. That is what defines metallic bonding, the sea of mobile electrons. Right? So mobile electrons are what makes the properties of a metal, right? Such as the good conductors, the malleability, the ductileness. That's definitely not a word. Being ductile, having luster. These are all from the mobile electrons. Intermolecular forces. Okay, so we have 3 different types of IMFs, or intermolecular forces. Right? So we have dispersion forces, we have dipole-dipole interactions, then we have hydrogen bonding. Okay. Okay, dispersion forces are the weakest type of IMFs, so they are in non-polar molecules, whether it's because of symmetry or because of the same electronegativity, and they're very weak because there's a temporary dipole sometimes. Out of nowhere, just and it's a very weak attraction. Dipole-dipole occurs in polar molecules, so whether it be a polar covalent bond or it be an ionic bond, because ionic bonds are polar. Yeah. I'm hoping that's right, because I can't think right now. Right? And these are strong attractions between polar molecules, where I lied, this is covalent. Pretend I never said about anything about ionic. I'm very tired right now. Oof. I never said anything about ionic. I'm so tired right now. Oof. So yeah, pretty much the partial positives attract the partial negatives. Yeah, because opposite forces attract. Then a hydrogen bonding, strongest IMF. So pretty much it happens when hydrogen bonds to fluorine, oxygen, or nitrogen, and the hydrogen becomes very positive. Very partial positive, and it's a very, very strong attraction force, the strongest IMF. Hydrogen bonding, it occurs between highly polar molecules containing hydrogen. So it's going to happen with hydrogen with water, hydrogen with water, hydrogen with oxygen, hydrogen with fluorine, or hydrogen with nitrogen, right? I guess those are the 3 ones. Disregard the part of the halogen. I don't know. I've never really studied that come up. So, oxygen, nitrogen, and fluorine. The strength of the electric bond. So because the hydrogen has a strong electronegativity. Actually, no. Wait. So pretty much the higher the electronegativity of, I think it means a difference. So no, it doesn't mean difference. So higher the electronegativity between whatever is being bonded to the hydrogen, so the right, that means it's gonna be a stronger bond. The higher the electronegativity of the element being bonded to the hydrogen, the stronger the bond. So like oxygen has 3.4 while fluorine has 4.0. So oxygen's gonna have has a weaker bond with hydrogen compared to fluorine with hydrogen. Right? So when what happens to hydrogen bonding? So they will have a high boiling point and a high melting point when there's a hydrogen bond. Regents question. Which of the following has the highest hydrogen bonds? HI, HCl, HBr, or HF? I shall wait. Okay, so the answer is HF. Why? Because, well, I mean, one way you can determine it is because. Wait, no. Is that a lie? That's a lie, because it's. Give me a second. No, it's not a lie. Well, because fluorine is one of the elements that forms hydrogen bonding, right? So that's one we can tell it's the strongest hydrogen. Strongest intermolecular force. But if you couldn't figure that out, you can figure it out because fluorine, out of all the four ones, has the highest electronegativity, right? Iodine has, I have no clue what iodine has. Iodine has 2.7, Cl is 3.2, Br क्या से? 3.0, and then fluorine has 4.0, which is the highest. So that's also one we can tell. But I would have just gone with, HF, hydrogen bonding, bada bing, bada boom. Dipole-dipole forces, which is also known as molecular ion attraction. Molecular ion attraction is when water molecules attract to ions differently depending on the charge, right? So when something is in water, then it's aqueous, right? And then molecular ion attraction is like with sodium and chlorine when it comes to water, right? Van der Waals forces or dispersion forces. This is also the weakest force. So van der Waals are very weak electrostatic forces of attraction between noble gases or between nonpolar molecules such as CO2. So this is why that gases such as H2, O2, and CO2 can be made into liquids and solids, and these van der Waals forces come from the formation of very temporary, very quick dipoles, right? But van der Waals forces are the weakest form of molecular attraction, right? So the condition for a van der Waals force to occur, it has to be a low temperature and a high pressure. And the way you can remember that is that you don't want to go to the beach when there's a low temp and a high pressure. That's not a fun day at the beach, okay? So pretty much the larger the molecule, you are going to need a stronger force, right? And then if there's more distance between the molecules, the weaker the van der Waals forces. I think that's very self-explanatory. Is that it? Oh, that's it. Okay, this is Unit 6. Unit 6. We have just finished Unit 6. Feeling great. Feeling amazing. Okay. Well, I hope you all have a great day, great night, great whatever. Wherever you all are. Yeah. Bye-bye.